So it will turn out not too hard to show that evaluated at NB. So basically what I want to do is this. I have S0 like this. And okay, h of NB minus I is S0 of NB minus I. I might be off by 1 here, just a second. Basically what I want is this. I basically want to be integrating S0 squared so that these are lined up as the same when k equals NB. And I don't quite have it, I'm off by 1. Okay, I think the error is that h of k actually equals S0 of k minus 1, not S0 k. And if that's true, then this is NB minus I plus 1, which means that when k equals NB, firstly I have S0 of, if I is 1, then S0 of 1 is 1, right there. S0 of NB minus I plus 1 is S0 of NB, which is there. That's 1. If it's 2, S0 of 2 is 1. S0 of NB minus 2 plus 1 is S0 of NB minus 1, which is 1, and so on. So that's correct. So it's not S0 of K, but S0 of K minus 1. So apologies for that, off by 1 error. And in the end, basically, so the idea of this filter is that when you take the sample, basically what you're doing is you're taking the signal, multiplying it by itself, and integrating. So that's how we select. That's how we select this filter. So basically, what we get is that this is equal to the sum I equals 1 to NB of S0 squared, which is 1 squared, which is equal to NB. Okay, what about, what's the outcome if 1 is set? The outcome of 1 is set is S1 of k, involved with h of k, evaluated at NB. Can anyone see quickly how anything changes here? Remember that S1 of k minus S0 of k. So that minus, this is equal to minus S0 of k, involved with h of k. So I could jump all the way to the end by saying scalars come out of convolution, but we don't necessarily have to. We can put that there, put that there. Now this is just a sum, and we definitely know that negative comes out of a sum. So we end up with minus NB. Okay, so the moral of the story. In the absence of noise, h of k is selected so that S0k involved with h of k evaluated at NB is equal to the sum over S0 of k squared. K equals 1 to NB. That's the optimal form of the filter. So this is really the take-home message. This is what we're going to show. So the challenge is to transform that into a linear impulse response, which, as you can see, is a problem because I screwed it up. I was off by 1 over here. But this is really what you need to do. Basically, you need to take the signal, multiply, do some signal processing that's equivalent to multiplying it by itself and summing it. And in a later class, we will show that that's in fact the optimal thing to do. That's the optimal thing to do in the presence of noise. So if 0 is sent, then we just showed that phi-j is equal to what? So phi-j is the filter output in the absence of noise. What is that? We just said this. It's ND. And if a 1 is sent in the absence of noise, it's minus NB. So what do you think a good threshold would be? 0. Sure, why not? So in the absence, if you know in advance that there's no noise, then you can pick anything between ND and minus NB. But it turns out that when we have noise, and 0 or 1 are equally probable, the optimal thing to do is to go exactly halfway between them, and that's 0. So in other words, if my filter outputs phi of j were equal to NB minus NB minus NB, NB minus NB, then my bit estimates, the at j, would be 0, 1, 1, 0, 1. Because remember, b hat j is derived from phi j by just examining the threshold. If it's above the threshold, we pick 0. If it's below the threshold, we pick 1. Okay, so that's what happens. That's a detector. That's how detectors work if there's no noise. So as you can see, they work quite well. What we're going to do for the rest of today is we're going to look at what happens when noise is introduced. So we're going to take the following approach. We are first going to take the approach of figuring out what the probability of error is. So we're going to try to figure out, regardless of what h is, we're going to try to figure out what the probability of error is. Now, regardless of what h and z are, we're going to calculate the probability of error. And then what we're going to do in the coming weeks is we're going to prove that this form of h that does this is actually the optimal thing to do. Sorry, this should be sum from k equals 1 NB of S0 squared. Okay, so let's think back to random processes.